Andrew, would you like to take the floor?
Yeah, sure. Can you hear me all right, Alex?
Yeah.
I'm going to take a little bit of a different angle and talk about sort of a systems mind frame. So I call this Life Finds a Way, and it's really tying a lot of themes that we've spoken about this morning, and I really love hearing people talk about these issues. So let me just throw this in present mode here. So my brush with nature, Andra mentioned this in the intro. My background is in biomimetics and biorobots, coming out of UC Berkeley. Worked on a handful of robotic startups. More recently, I've been working on agricultural robotic systems, from greenhouse autonomous vehicles for imaging to automated soy weeding, looking at soy, and more recently looking at biosensors that we can put in the field to do fungal pathogen detection. So what's sort of been my takeaway from all these projects so far? Nature is messy. And I think that's something that a lot of us have touched on here today. But it's beyond just the harsh conditions that we see in the field. We've talked about robustness and difficulties with mud and how to clean equipment and how to make things robust. It's fundamentally
Andrew, I'm afraid we just lost you, describing nature is messy.
That farms are complex adaptive systems. We're dealing with, and especially as engineers.
Oh, you're back.
Let me know when I'm back. I'll just keep.
Yeah.
Oh, okay, I am. Okay.
You're saying nature is fundamentally messy was the last thing that we got coherently.
Oh, okay.
I'll agree. Just about 30 seconds. 30 seconds.
Okay, great. Sure. So yeah, nature is messy. And I know we've touched a lot on how do we make these systems more robust and withstand the harsh environments. But beyond that, biology and farms specifically are really complex adaptive systems. And that's really what I want to talk about for the next few minutes. So what does that mean, complex adaptive system? It means that there's lots of discrete components or agents that are highly networked. It's a system that operates at multiple size scales. And because of that, you see highly nonlinear effects that are very difficult to predict. And you see emergent behavior that you wouldn't discover if you study these systems in isolation. So what does that mean for us as engineers? It means it's difficult to predict and also difficult to control. So, I think a lot of folks have pointed at some of the challenges in current industrial agriculture, and the thing I've been asking myself is like, why? How did we end up there? And potentially, it comes down to almost a mindset that we take this classical engineering approach into this domain, and we try to reduce the problem, break the system down into its subcomponents. And our mental model for these environments is manufacturing, where you finally isolate and control every step in the chain, and you deal with those, and you drive each of those to the greatest efficiency. And this, as engineers, this is what we're taught. And I think it's obvious that we're reaching our limit to this approach. We're seeing that nature is reactive, not static. Is that any time that we pose an action to the system, we have to expect that there's a response there. And we have these very non-intuitive responses from the ecosystem. When we're trying to force something into this non-equilibrium state, there's often higher costs that come from forcing it into that non-equilibrium state. And there's many examples of this. You can look at soil erosion depletion, disease outbreak in monocrop and animal ag systems, algae blooms caused from overuse of fertilizers, and also pesticide and herbicide resistance, where you see these incredibly pesticide, herbicide resistant weeds taking over fields, and the farmers are almost helpless to stop it. So I'd like to start conversations around can we come up with a better approach, and how do we act when we come to an understanding that we are fundamentally operating in a complex adaptive system? How can we start having considerations of system level goals? How can we start thinking about measurement as being continuous so that we can get a pulse on what's actually happening in the ecosystem? how can we start focusing on interactions in relationships instead of subcomponents? And then how can we not take for granted that our actions are going to result in a specific outcome? And, you know, Ken talked about this with the Alpha Farm system. I think there's lots of great examples and pilots being done in regenerative agriculture, permaculture, polyculture. All these things are looking at these sort of system level goals. So the work that I'm doing right now at a company called Root Applied Sciences, we're focused on starting on the sensing side and looking at bringing sensing really to the biology level, looking at DNA and RNA analysis and understanding what's happening in the field in real time. So we're looking at real-time distributed sensing, hopefully enabling precision spraying of pesticides that you can't detect visually. And then when we network these things, we can start to form more of an ecosystem response. So, you know, looking to the future, I'd love these conversations around sort of system level design. And I think a lot of the panelists today are talking about technologies that capture the nuances of not broad, taking broad acre systems, but considering the micro ecosystems and plant level considerations there. And you know, I think automation has a huge role to play in scaling these approaches, because although these approaches in regenerative agriculture, I think are pointing the way to more sustainable, more secure food systems, there are challenges in labor that are associated with the attention to detail it takes to execute on that. So that I'll wrap it up to that, and happy to dive more into Root or other topics that folks might have questions on.
Thanks a lot, Andrew.